just a few announcements. So like homework 4 that's out now, due next Thursday, submitted Wednesday for bonus point. And a lot of the questions are going to involve writing answers using tables. So we've actually put together a guide for you that just tells you a little bit more about how to best use tables in your answers. And we'll have that on Piazza later today. So look out for that. Project 1 is out today as well. And it's basically like a longer homework assignment. You can get a partner in lab for that. And basically it's kind of split into 2 submissions. So you have your checkpoint, which is due next Friday. And then you'll have the actual project itself, which is due the following Friday. So that's kind of how projects work. Sorry, let me just quit a few of my apps here. Still not getting notifications. Cool. All right. So yeah, sorry, I don't know why this is Friday here. So maybe a little bit out of date. But basically today we'll kind of review what we started with functions. We'll talk about how you can actually apply a function that you made to like all the rows of a table, which is going to be very useful for us. And then we'll go a little bit more into groups, which is the group function is something we've used before when we were trying to visualize like the categorical distribution of a variable. And so we'll just go in a little bit deeper to how do you actually use groups. There's more powerful ways that you can use it than just that. And that's kind of where we'll conclude the lecture. And then we'll also do a really fun example today that combines kind of everything we've been doing in terms of like table operations and visualization, so all at the same time. All right, so for functions, we talked about how we've been using functions throughout the class, and so we talked about how there can be situations where you might want to write your own functions, and so we showed you how to do this. Last lecture, basically the way it works is you say def, and then it's the name of the function, and then you have the argument names. So this could be one argument, it can be multiple arguments. In this case, this function just has one argument, which is values, and then you have kind of the body of the function, which is what the function actually does with those arguments. And then sometimes your function has a return statement, and so this is called the return expression, and so that means that the function is going to return something back at the end of it. There can also be functions that don't return anything back. They just kind of do something, but then they don't actually return anything. So you'll see kind of both of these. So let's actually go to the demo and go through some of these, some examples of functions that we've made. So first of all, let's look at like how do we do a function with one argument. So if we want to do this, right, let's create a function. Let's say it's called age. So we want to figure out what's the age of somebody given that we know, what year they're born in. So we could do def age, and then our argument, let's call it year. And then if you want to figure out what their age is, we'll just do 2020 minus year. And then we'll just return that. And so this could be one way to write a function. Oh, it looks like I didn't run the first cell, thanks to the reminder. So now we have a function written out here, and it's kind of the body is split up into 2 lines. So the first line, what it does is it takes in our argument, which is year, and then we subtract that from 2020, which gives us essentially the age of the person, and then return the age. So again, year here is an argument that someone is going to pass into this function when they want to use it. So I'm calling it year, but you could call it whatever you want. So you can name the argument whatever you want, but you typically want to name it in a way so that's kind of easy for people to read. That's basically the way to think about it. And so now that we have this function written out, we can actually use it. And so how do we use it? We just write age again, and then we can pass in a year. So let's say we pass in like 1991, that returns 29. Or we could do like 1942, which is the year that Joe Biden was born, and you can see his age. So there's different, that's like one example of how to use this. And then you could also just put all of this on one line. So we talked about this last time as well. So if I wanted, I could have defined the function so that it just returns 2020 minus year. You can do that too. But again, sometimes it's nice to split things up into steps. Typically is going to make you less likely to make mistakes and also makes it a little bit easier to read the code. So that's a function with 1 year, or sorry, function with 1 argument. And then we can also make a function with 2 arguments. So we can show you how to do this. So let's say we wanted to make this function a little bit more interesting. So let's call this name and age. And then what the function is going to do is it's going to take in a name as a string and then also the year that you were born. And it's going to return a string that says someone is however many years old. So basically what we want to do is we have name and age. So first we want to get, or sorry, we have name and year, and we want to get the age of the person and return that as a string along with their name, essentially. So we could do return name plus is, and then let's convert the age into a string. And so we already have the year here, so we can convert it into an age using the other function that we've made already up above. And then this will kind of respond everything together. So I'm just doing everything in one line here, just to kind of make it a little bit simpler. But basically, if you have year, which is the year they were born, the name as a string, this function is going to take the name, then add is as another string, and then the string of what their age is. And we already have this function called age up here, so I don't need to write 2020 minus year over here. I can just call the age function, and it'll already do it for me. And we have str here because we want to convert it into a string so that all this can be kind of together as one long string. So let's just see an example of it, and then we can go back to how it actually works. So for example, if we do name and age, let's pass in Joe as a string, and then the year he was born, 1942. Then it spits out Joe 78. So how did it do this? It took this first argument, Joe, it assigned that to the name in this case, and then it took the second argument, 1942, assigned that to year. And then what the function did is it said, okay, I need to return whatever's in name, which is Joe, plus this string, which is it is with a space before and after it, and then plus another string. And what is this other string? Well, it's saying take whatever's in here and convert it into a string and add that to these first 2 strings. And so what is inside here? Well, this is saying call the age function on whatever year is. So in this case, the year is 1942. So if we call the age function on it, it converts that into how old the person is, which is 78 in this case. And then it converts 78, which is an integer, into a string. And so now you get everything as a string together. And then someone asked, could you add additional strings after this? Yes, so you could add additional string here that says years old if you wanted. So I can make that the function, and now if I run it, now it says Joe 78 years old. So that's fine too. Everything up to here is a string, so that means you can add additional strings to it if you want to. Why does the year also need to be a string? So the year actually is not a string initially. The year is just an integer up here, but then we converted it into another integer, which is the age. And then what we said is we wanted to add the age into this string. And if you wanted to add, if you want to combine like an integer with a string, you need to first convert it into a string as well. If we didn't have this str here, then we'd get an error because Python wouldn't know how to add a string with an integer. So that's why we convert it to a string. Okay. Yeah, okay. I think we'll move on to the next part. So that's kind of functions. So again, functions can have one argument, they could have multiple arguments. They could also have no arguments. We'll see a few examples of those that we make ourselves, but for the most part, in this class, we'll usually have arguments in the functions. And so next up is apply. So there's going to be a lot of situations in this class where we're going to have this function that we've written. And right now we had some examples of using that function on like one person, right? So we talked about Joe and we figured out what's Joe's age. Now, what if I had a bunch of individuals in the table and I wanted to know all of their ages, but I have them in like year format? I want to convert that to age and make some string that says their name for every single person in the table. So this is going to be really common where we're going to want to do an operation to everybody in the table, and that's where apply is going to be useful. And so it's actually its own method called apply. This is kind of how we use it. And so the way it works is it basically creates an array by calling that a function that you specified on every element in a specific column that you also specify. So the way apply function works, the first argument to the apply function is actually the function you want to apply. And then the other arguments are the other columns that you want that function to be applied to. So here's kind of how it is written out. So here's an example. Like if you have some table, you put the table name here, then you do dot apply, and then pass in the function name as the first argument. And then the second argument is going to be the actual label of the column that you want this to be applied on. And so that's going to be a string. And then if you have a function that takes in multiple arguments, then you're going to have to pass in, kind of specify that there's multiple columns that it needs to be applied on. So we'll see some examples of this. Okay, so here's a table I've created here just kind of randomly. So it's a table called staff. It has a column called employee with a bunch of names, and then it has a column called birth year with a bunch of years, which is the year that they were born. So if I run this, we can take a look at this table here. So we have our employees here on the left. We have the year they were born on the right. And so we want to apply some function to these. So one thing we can do as a good example is let's make a function that just returns their name, but makes it a little bit more interesting. So for example, I could say, let's call this function greeting, and it's going to take in a name, and it's going to return, this is name. So for example, if we did like greeting Jim, it just returns this is Jim. Oh, okay, so this is a good example actually where we might want to change our function. So it returned this is Jim, but this is squished with Jim. So we should add a space here to make it a little bit nicer. So let's rerun this. Now it looks a little bit nicer. And then we can make it even better actually, because this is kind of like a generic greeting, but let's make this a little bit more special. So let's do Dunder Mifflin. This is blank. So now it's a little bit longer, and then we can try it with another example. So you can do Dunder Mifflin, this is 10. So here's a function. Okay, cool. So we have a function here. It takes in one argument. It returns kind of a fancier string with that person's name. So if you want to actually apply this to the entire table, we can do that as well. So we could do staff.apply. So again, staff is the name of our table. We call .apply on it. The first argument to apply is going to be the function we want to run. So we'll do greeting. And then which column do we want to run it on? We want to run it on employee. So we pass in employee as a string. And so now you see that this runs this function greeting on every employee in our table. And so it returns it as an array. So that's kind of the format that it returns it in. And then if we also wanted to write a function that works on multiple arguments, we could run that on the table as well. So let's say we wanted to use that function we made earlier, which is name and age. So we could do that as well. But if you recall, name and age is a function that requires 2 arguments. So let's just scroll up and take a look at it. So name and age requires 2 arguments. You need the name of the person and then the year they were born. And so we need to specify that in apply as well. We need to tell apply that, okay, I'm going to apply this function on this table, but I need to know which column is going to be the name, and which column is going to be the year. And so we can do that here. We just list them out in order, essentially. So we know that employee is what we want to be associated with name. And then what do we want to be associated with the year? It's going to be the birth year column. So we can write that here. And so this is how we would apply a function with multiple arguments onto a table. And so now if we do this, it spits back these results. So we get Jim is 35, Dwight is 32, and so on. So these numbers are made up. Creed isn't 116, but just an example of how this works. Where did the name and age function come from? So the name and age function was something that we specified up here. So when you run this cell here, def, name, and age, and then whatever it does, this kind of saves it into Python. So like in that instance that you're running Python, it's going to be now saved there. So if you now try to use that function in any other cell below, you'll be able to use that function. And that's kind of the point of the function, is like we write it once and then now we can use it again and again. Okay, so let's continue on. So that's apply. So now we know how to make functions. We know how to run a function on kind of every row of a table. And so let's actually put that together. So for this next part, we're going to be talking about a data set that was kind of actually put together by Sir Francis Galton. So he was a pioneer in making predictions and just statistical analysis. Did a lot of work in heredity, but also did some stuff that was pretty terrible. And happens to be related to Charles Darwin. It's kind of a fun fact about him. And so he studied a lot just about how, like, traits about people like get passed down to the next generation, things like that. So we'll take a look at some data that he collected and see if we can make some predictions out of it. So we have this data set already in a CSV called galton.csv. So we'll just read this in. And here's what the table looks like. So we have several different columns here. So this first column is family. It's just kind of an indicator of which family that individual is in. Father is the height of the father of this individual. So each row, first of all, is an individual in this data set. So there's roughly like 1,000 or so, a little bit under 1,000 individuals in this data set. And so, yeah, the family column tells you which family they're part of. Father tells you the height of the father in inches. Mother tells you the height of their mother in inches. So if you look at these first four people, these are essentially these are four children in one family. And so that's why they have all the same exact mother height, all the same father height. And then we also have mid-parent height. So mid-parent height is a weighted average between the father's height and the mother's height. And so weighted average meaning that it's not exactly like just add them both up and divide by 2. There's some more weight given to one parent's height compared to another. So that's mid-parent height. And then children just tells you how many children there are in that family. So this first family here, there's 4 children there. And then child number is kind of the order in which the child was born. So we have 4 individuals from a family here who are 4 children. And so this just tells you like, this is the first child that was born, the second child, and so on. Then we have also the gender of the child. And then we have the child height, which is essentially what was their height when they grew up to become an adult. So once they became adults, what was their height? And so we're going to try to study the relationship between the father and the mother's height and see if we can find a way to predict what the child's height is going to be once they become an adult. And see if there's any way we could actually do that. What does the family column refer to? The family column is just kind of an indicator of a family. So it's like these 4 people are from family 1, these 4 people are from family 2. So the order of the numbers actually doesn't matter too much here, but it's just saying like that's a unique way to identify the families. Yeah, that's a good question. Is the parent height, is this related to like their height initially at some period in time. So this is kind of when they were all fully grown adults. So this is gonna be the height of the father when he's a fully grown adult, height of the mother when she's a fully grown adult. So you're not like growing anymore, basically, you know, at some standard age. And then the child height is gonna be the same thing. So it's gonna also be a height when they're kind of fully grown. So. And yeah, that's a really good question. So someone said, does this mean that family is categorical here? Yes, that's correct. So family is essentially categorical here because family two being greater than family one, like there's no, that doesn't mean that they're greater than or something like that. It's just they're different family. So, and then mid-parent height, yeah, good question. So mid-parent height is just weighted average between father's height and mother's height. All right, so let's actually do something interesting with this data. So first thing we want to do is we want to look at the relationship between, let's say, mid-parent height and child height. So what's a good graph that we could use to visualize that? Cool, scatter, yep. So we can do Galton.scatter, and then let's do mid-parent height. Hope I spelled this right. Yes, okay. Mid-parent height and child height. All right. And so here we have mid-parent height on the x-axis, we have child height on the y-axis. And so it's interesting, you can see kind of when the mid-parent height is like slightly larger, it seems like child height also tends to be a little bit larger. And then, you know, inversely, like when mid-parent height's lower, typically child height tends to be lower, but not always. Like if you had mid-parent height around 65-ish, they did sometimes have kids that were like all the way up to almost like, I don't know what this is, like maybe 68 or something like that. So, you know, there's still kind of a lot of spread here, but in general, you can kind of see a trend, you know, things seem to be kind of going up and to the right. So this is kind of one way to visualize this. And so one question you could ask is, let's say you know that the mid-parent height of somebody is 68 inches. Like we just pull out some new person who we don't know what their height's going to be when they become an adult. But we do know that the height of their mid-parent is 68. And so we want to find a way to maybe predict what their height is going to be when they become an adult. And we'd like to use this data set to do that. And so one way we can do that is, well, we can try to look at other individuals who also had a mid-parent height similar to yours, so like similar to 68. And so we can try to visualize this as well. So we'll do Galton.scatter, and then we're gonna add some reference lines here. So you don't need to worry too much about how I'm doing the reference lines. But it's just a way to kind of add some additional visuals on here to make it a little bit clearer. So we'll do 67.5, 50 to 85, and the color is red. And then we'll do another line at 68.5. So I'll just write this out and then I'll explain what it's actually doing. So basically this first line, what it's saying is, let's plot a line at x equals 67.5 between 50 to 85. So that's what we did here. So x equals 67.5, and we drew it from 50 all the way up to 85. And then we did the same thing at x equals 68.5. So now we've drawn two lines kind of around 68. And so the idea is, if we have someone new who we know their mid-parent height is 68, if we wanted to make a guess for what their height should be, it seems like their child height is probably going to be somewhere in this set of points here, given this data set. So this is one way we could make a prediction using this data set. And the LW equals 2 is just specifying how thick the line is. It's like line width, essentially. So again, you don't need to worry too much about how we actually did this. You don't need to know how to do this for this class, but just explaining it. Okay, so now we kind of have an idea of how to look at people nearby you. And so what we'd like to do is actually calculate the average height of the people within this region. Because that seems like if we had to come up with one number for what we think your child height's going to be, given that we know your mid-parent height is 68, it seems like taking the average of people who are looking like you was a good idea. So let's actually do that. And let's see what our prediction would be if we did that. So firstly, let's take everybody who's nearby you and put that in its own table. So we'll do nearby equals Galton dot where mid-parent height. And we can say r dot between 67.5 and 68.5. So that's going to take our Galton table and then return just the subset of the table where the mid-parent height's between 67.5 and 68.5. And then we'll calculate the average child height of those people. So nearby mean is nearby dot column child height. And then we will take the mean of that. So mean is the average. And then we get nearby mean. So in this case, what this is saying is that of the people who have a mid-parent height between 67.5 and 68.5, their child height is 66.2 inches, so on average. And we can actually visualize this now on the plot above. So let's take this plot. I'm just going to copy that, paste it down here. And I'm also going to add a point right at 68, which is going to convey what our prediction would be. So 68 nearby mean. We'll also color this red. And then the size would be 50. Again, don't need to worry about what that means. But this just allows us to visualize the prediction. So now we can see the prediction here as a red dot. So essentially, if your mid-parent height is 68, our prediction for your height is going to be child height. Is going to be 68, sorry. Or 66.2 actually, sorry. 66.24. So this is kind of the prediction for somebody who is 68 mid-parent. So yeah, let me just show you this code again really quickly. So just to recap, we had Galton. What we did was we said, let's take just the rows of that table where the mid-parent height's between 67.5 and 68.5, because we wanted to convey that we're taking people that are around 68. And then once we have those set of people, then we said, okay, let's just calculate their average child height. And that ends up being our prediction for somebody who we know is 68. And you do not need to know how to make the red line and the red dot. Okay. So now that we have that, we've made a prediction for somebody who we know their mid-parent height is 68. But what if we want to be able to make this prediction for just kind of anybody? Or maybe we just want to actually try it out on our data set. Like we have all these individuals, we know what their child height actually is, but it'd be interesting, like what if we made a prediction using this algorithm to see how well we do on the people in the data set. Like let's imagine we didn't know what their child height is, and we want to use this algorithm to kind of guess what their child height should be. And we want to run that on everybody in our data set. So how would we do that? What could we use to do that? Yeah, so people are saying write a function, use apply. So it's basically both. So we want to first write a function that allows you to make a prediction on any individual. Once you have that function, then we can use apply to actually run the function on everybody in the dataset. So first of all, let's actually make a function that just predicts your height based on your mid-parent height. So let's call it predict, and it's going to take in your mid-parent height. We'll just call it h, this function, just because there's a lot that this function does. So I don't want to type too much right now. And essentially what we're going to do is it's basically just this logic right here. So I'm just going to copy that and paste it back down here. So essentially the first line is, we'll take nearby. We want nearby to be equal to Galton, where mid-parent height is between, we'll do h minus 0.5 and h plus 0.5. So now we're trying to make this more generic to just any mid-parent height, not specifically 68. So we'll do h minus 0.5 up to h plus 0.5. And then we can just return actually this calculation here. So we just return nearby dot column child height and then the average of that. So this allows us to run a prediction on pretty much any height that gets, any mid-parent height that gets passed in. So let's actually create this function and then we can actually try it out. So first of all, it might be good to try it out on a value that we already ran further above, which was 68. So if we call prediction on this, we get 66.24, which is what we had before. We could also run it on somebody who maybe has a mid-parent height of 70. So now notice how the prediction for them is a little bit higher. You could do someone who's had an even taller mid-parent height of 73. Then our prediction for them would be 69.5. So you can see how as their mid-parent height is going up, our prediction for what their child height is going to be also seems to be increasing. So that's kind of interesting, but probably makes sense with your intuition. And yeah, so just to review the prediction function, because it got a little bit cut off here. Actually, I can put this to the next line, so it's a little bit easier to read. So essentially, the first line of the function says, okay, you've given us this mid-parent height, h. What we're going to do is we're going to take the Galton data set. We're going to find everybody who has a mid-parent height between h minus 0.5 and h plus 0.5 and assign that to the value nearby. And then what we're going to do is take everybody in nearby and calculate their average child height. So that's essentially what we're doing here. And so mean is a function. Someone asked, why is there this parentheses here? It's a function, so you need to have a parentheses here. This is an example of a function that takes in no arguments. So this function just takes the average of whatever is here. It doesn't need to have any arguments specified to it. Does mid-parent height need to be on the next line? No, it doesn't. I just put it on the next line here just so you could read everything, but you can also just have it all on one line as well, like this. The only problem is then like this gets cut off here. So I have to kind of scroll to the right for you to be able to see everything. So that's the main reason I did that. But it doesn't need to be on the next line. Cool, so now we have our function. What would be nice to do is actually run this function on everybody in our data set. So run the predict function on everybody. And again, this might seem a little bit silly because we already know everybody's height, but it's still interesting to actually run this function and see how good does this function actually do in terms of predicting people's heights. And so we can do this using apply. And so let's actually do this. So we'll do Galton.apply, and then what function are we going to apply? We're going to apply predict, and then which column is it going to be applied on? It's going to be applied on mid-parent height, because that's what we're expecting as the input. And then let's actually assign this to a name, call it predicted heights, and then you can also take a look at what it actually is. And so if we run this, it's going to take some time to run because it needs to apply this function to all the columns or all the rows. It's like almost 1,000 rows in this data set, so it takes a little bit of time. But now we have a result, and so we can see the predictions now for every individual in this data set. And this is in an array format. Now, this is a little bit difficult to read, so I think it might be nice to actually visualize this in a graph, and we can do that. So what we can do is, let's first add these predicted heights back into the Galton table. So let's do Galton equals Galton with column. And we're going to call this new column predicted height, and we'll pass in predicted heights. And so we can just take a look at what that table looks like now. So all we've done is we've had our Galton table, we added a new column here, predicted height. And so we can see here this first individual, their actual height was 73.2, we predicted 70.1, so pretty close. If you go further down here, you know, someone who's 73.5, we predicted 70.4. So what's something kind of interesting that you might notice here? You guys see any interesting patterns here with these predictions and like how they relate to, you know, the characteristics of the individuals in the data set? So yeah, same for the family. So it seems like everybody in the same family gets the same prediction. The reason for that is because our prediction takes in the mid-parent height, and the mid-parent height is the same for everybody in the family. So their predictions are the same for that reason. Yeah, females, it seems like we are predicting a height that's like taller than what their actual height is. It's kind of interesting. Seems like for males, it's the opposite. So for males, it seems like we're always predicting like less than what their height actually is. So that's kind of interesting too. So yeah, those are very interesting insights about this. And so let's actually visualize all of this in a plot. So we'll do Galton. Let's just select the columns that we want. So we'll do mid-parent height, child height, and predicted height. I'll explain why I'm selecting the column, just these columns in a second. And then we'll do dot scatter mid-parent height. And so what we see here is we have mid-parent height on the bottom, but now we're actually plotting two things on the top. So we're plotting child height in blue and predicted height in gold. And that's why we did select. So if you call scatter with just one argument, what it's going to do is it's going to plot all the other columns in the table against the one that you specified. So what this is saying is whatever table you have before scatter, plot everything against mid-parent height. And our Galton table has like a lot of columns. We only wanted to plot a few of them against mid-parent height. So that's why we selected just these three columns. And so now what happens is when you select just these three columns, you get a table that just has mid-parent height, child height, and predicted height. We call scatter and pass in mid-parent height into that means plot these two guys against the one that we specified. So it just makes the plot a little bit easier. Otherwise, we would have had like 10 variables plotted here and it would be kind of confusing. And so you can see here, it's pretty cool. This gold bar seems to be going kind of, gold line seems to be kind of almost going through the middle of this kind of cluster of points, which is pretty cool. And then this is how you can interpret this. So basically, if somebody has a mid-parent height around 73.5, their prediction is going to be a little bit over 70. But clearly, as we can see, there were individuals who had a really wide range of heights. So the prediction does a good job, but it's not perfect, obviously, but it's pretty decent guess given kind of the data that we have. So the y-axis here is actually showing two variables now. So we have child height, which is in blue, and then predicted height, which is in gold, which is kind of our guess for what their child height should be. And then mid-parent height is on the bottom axis here. So basically trying to compare child height against mid-parent height, and then also comparing predicted height against mid-parent height. So it's kind of two separate plots, but overlaid on top of each other. And how did we overlay both plots? So first we took our table, we selected just three columns that we mainly wanted to focus on. And then we said, let's do a scatter plot of everything against mid-parent height. And so that's kind of what we did. And so another thing, now that we have predictions, another thing that may be interesting to look at is, how good is this prediction? So that's another useful exercise as well. And so if we want to know like how good these predictions are, typically what you do is you take your predicted value and then subtract what the actual value is. And that gives you a sense of, what your error is, or like how inaccurate you are. So we can actually create a function to help us do this. It's gonna be a little bit simple, but we'll call it difference, and it's gonna take in two values, and it's gonna return x minus y. So this is gonna be a function. The reason we're writing this as a function is so that we can apply this to the entire table. And that allows us to visualize the errors. So let's actually create something called prediction errors. And this is going to store kind of how different the prediction is from the actual value. So we'll actually use apply to do this. So we'll do Galton.apply difference. And which two columns do we want to apply it on? We want to apply it on predicted height as well as child height. So let me just put this on a new line so you can see it all together. And we can take a look at the errors. So this one actually runs pretty quickly. And so here we're taking difference, again, passing in predicted height and child height. So what this is going to do is it's going to calculate predicted height minus child height on everybody in our data set. And so now we have the actual errors of our prediction. And so once we have the errors, we could again add this to the Galton table so that we can look at everything together, because that tends to be the easier way to look at everything. So we'll do Galton equals Galton with column errors, do prediction errors here, and take a look at what this looks like. Ooh, a typo here. So now we have a new column at the end called errors. And so we can see for this first person, our prediction was 3.1 inches lower than the actual height. For the second person, the prediction was 0.9 inches higher, and so on. And so again, here now it becomes very easy to see a lot of the differences between like the males and the females. So look at all the males, all the predictions are like negative. So all the predictions are lower than the actual value. And for females, it's the opposite. So we can see that difference there. And then we could even actually visualize the errors too. That's always kind of helpful thing to do. And we're gonna do this more later on in the class. But if we take Galton, we could make a histogram of the errors to look at the actual distribution of the errors. And so this is kind of what the distribution of the errors looks like. And so our predictions looks like sometimes we're off by like as much as almost 10 inches. Most of the time we're actually within about almost like 3 inches or so, it seems like. So it's actually pretty good. But sometimes we do have some pretty big errors. And then what's also kind of interesting is we could look at the histogram of the errors based on the gender of the person and see if there's any difference there. So we could do histogram of errors and then group by gender. So this is kind of a new way to use histogram. But basically you can specify what you want the histograms to be grouped by. And so in this case, we're grouping by the gender column. And so now we can actually see the histogram of both of these different groups of the table. And so here we have females in blue and the males in gold. And so you can see here that most of the errors for the females are actually positive, which kind of works with our intuition that we were seeing that it seems like it was predicting heights much higher for the females. And then for males, it was negative, or essentially meaning that we're predicting lower. So this is kind of one way to visualize that. And then this darker yellow section here is just kind of where the histograms are overlapping. So that's just a way, they're both shown with some transparency so that you can actually see them overlapped on top of each other. Okay, so we'll actually skip the discussion question for now. I just want to go over grouping because we don't have that much time left. But basically, groups is something we've used so far a couple times. We've used it to visualize categorical distributions. And essentially the way it works is we talked about how, it takes in, you take your table, you call group on it, and then it takes in what column you want to group on. And what's going to do for that column is it's going to find all the unique values and count up how many times they show up in the data set. But actually group is more powerful than that. You can do something more than just count up how many times each value shows up. So the actual way to use group kind of even fully really is your first argument is which column to group by, but your second argument, which is optional, and we didn't actually specify this up until now, is how you want to actually combine the values. And so by default, it combines using len, which is just counting up the number of times that value appears. But you could also list out all the values as well, or you could actually take a sum of all the group values. So there's kind of slightly different ways to use this, and we'll see some examples right now. But basically group is a little bit more powerful than what we've been using it for so far. So let's see some examples of this. So let's read it in a table that we have on ice cream cones. So we've seen this one before, I believe. So it has 3 columns. First column is kind of the flavor of the ice cream. Second is kind of the color. And the last one is the price. And so these are a few different ice cream cones that we have. And so we could group by, let's say, flavor. So we could do cones.group flavor. And this essentially allows us to view the categorical distribution of flavor. So it counts up how many times each of these values shows up. So bubblegum, there's basically 3 unique values of flavor: bubblegum, chocolate, and strawberry. So bubblegum shows up once, chocolate shows up 3 times, strawberry shows up 2 times. And so this is one way to use group, which we've kind of seen before. And then what you can do, which is a little bit more powerful, is you could do, you could specify exactly how you want to group it. So instead of just counting up how many there are, you could actually do np.average. So if we do that, if we do this, what this will do instead is it's going to take all the other columns in the table and then calculate the average value of them for each of the flavors. So for example, for bubblegum, the average price is $4.75. For chocolate, the average price is $5.08 because chocolate appears 3 times here. So it basically averages up the price column. And we don't see anything for color average because Python doesn't know how to take the average of a categorical variable like color. So that's kind of why it just ends up being blank. And so one thing we could do is remove the color column before we actually do the grouping. So we could do cones.drop color and then do the grouping. And so this is a little bit easier to read. So basically we have the unique values of flavor just like we did before, but now we have their average price shown up here. And so this is kind of a more powerful way to use group. It's a very common way that we'll use it in this class too. You could also try a different function. So let's say I wanted to know like what's the minimum price for an ice cream cone for each of these flavors. So I could do that too. I could just pass in min instead of np.average. And so then we see something like this. So this is another way to use it with kind of multiple, or with an additional function. So when we say that the len is the default function, what that means is if you don't specify anything, then it just counts up how many times each of these appears. So len is a function that's used on arrays to count up the length of an array. And it's essentially how it's applied here, essentially. So it just counts out the length of how many times bubblegum shows up rather than counting up like the average of another column or anything like that. Cool. Okay, so let's see. We have a few more minutes left. I guess I can do a few more examples I think would be helpful of using group on our welcome survey that we went over last time, just so you can get a better idea of the different ways that we can use this. So let's say we have our welcome survey and we want to group it by, let's say extroversion. And I want to know like the average value of all of the other columns. So actually, let's just take a look at this real quick. So we had this welcome survey. It has these 6 columns: extroversion, number of people you text, how many hours you sleep, whether you're right-handed, left-handed, or both, which leg do you put in first when you wear your pants, and how do you sleep. And so let's say we want to look at how these other variables maybe relate to extroversion. And so one thing we could do is we could group by extroversion and look at the average value of the other columns for each unique value of extroversion. So we could do survey.group extroversion and pass in np.average. And then let's actually take a look at what this is. So in this case, what group is doing is it's going to return this first column, which has all the unique values of extroversion, and that it's going to calculate the average value for all the other columns in the data set. So we can see the number of texters, textees, I guess, on average for each value of extroversion. You can see the average hours of sleep for each value of extroversion. And then for these 3 columns, we get blanks because they're categorical. So Python doesn't know how to calculate the average of the categorical variable. So that's why these are all going to be blank. But these are pretty interesting here. And so it might be useful to actually plot this in a similar way that we just did that plot with the child height and the predicted height. So we could plot maybe these 2 columns, textees and sleep, against extroversion, against the unique values of extroversion, because that might be kind of interesting to just visualize this relationship a little bit better. So we can do that. So we could do by extra, which is the name that we gave to this new table. And then I'm going to just select the first 3 columns because these last 3 columns are all blank. And we'll plot everything against extroversion. And so again, we're doing plot here because this is going to be a line plot. And a line plot makes sense because all the values on the x-axis have this like unique, that they only appear once in the table. And so here we can see kind of for each unique value of extroversion, what is the number of textees, as well as what's the hours of sleep on average. And so just to recap what we did here, we grouped our entire table on extroversion, which means that take all the unique values of extroversion and then do something with each of the unique values. In this case, what did we want to do? We wanted to calculate the average of the other columns for each unique value of extroversion. And so that's what we did here. And then we plotted everything against extroversion with this line of code here. And so I did select 0, 1, 2 to specify that I want to just select these first 3 columns. And then we plotted everything against extroversion. So this is pretty interesting result here that you're seeing, although maybe not that surprising, but people who are more extroverted tend to text more people on average. So not like completely surprising. But what's also interesting is this hours of sleep. We can't really tell the trend here. There might be a trend, maybe there is not, but it's hard to tell because it's so like small, like squished in the graph because of this other variable that's like changing so much. So what we could do is just plot just that hours of sleep and ignore the number of textees. So if you go up here, hours of sleep is this one over here, that third column. So let's actually just remove the second column. And this will allow us to plot just hours of sleep against extroversion. And so this is pretty interesting. We see this kind of almost like a U-shaped plot. So like really extroverted people seem to be getting a lot of sleep actually, almost that 8 hours that we recommend. And then it's like kind of low here, and then looks like super introverted people get a little bit more sleep too. Not sure why exactly, but that's at least what the data shown. That's kind of interesting to be able to see the differences there. And it's actually surprising because last semester, the really introverted people got actually the least amount of sleep from everybody. So it was kind of like all the way down below the graph and then went up. So that's good to see that people are getting more sleep in general. But yeah, this is kind of a way that we can visualize this too. And so we can group by more than one column. We didn't get to cover it today. I think we're a little bit out of time, but we'll try to get to that next week. But this is kind of how we at least group by one column. And hopefully that's a little bit clearer.